Welcome to Steward Observatory and the Steward Observatory Public Evening Lecture Series, started in 1922 by Andrew Ellicott Douglas. And we're happy that we're still keeping it going, almost 100 years later. We also welcome those of you who are watching this podcast on iTunes U or at www.as.arizona.edu. Welcome to you as well. Before I introduce tonight's speaker, I would first like to remind any students in the audience, if you're here for an assignment, I will validate your assignment at the conclusion of tonight's lecture. Also, the telescope is open tonight for public viewing. Yes, we have good weather. So it's the white building right next door. I also would like to bring to your attention a further schedule. This Thursday, we're having the Phi Beta Kappa Visiting Scholar Lecture here at Steward Observatory. That's because I'm president of the local chapter of Phi Beta Kappa. Francis Su has a talk on mathematics for human flourishing. He's from the Department of Mathematics at Harvey Mudd College. Our next Steward Public Evening Lecture is actually February 17th. Because the College of Science will be having their lecture series starting in February on Tuesday nights, we're kind of going light in February. So our next lecture on Monday night will be 3 weeks from tonight, when Yancey Shirley will talk about 50 years of radio astronomy in southern Arizona. But without further ado, I'd like to thank Professor George Rieke for stepping in when our original speaker for tonight canceled. So George Rieke is a Regents professor, which is like the highest honor of professor you can have here at the University of Arizona. He received his bachelor's degree in physics from Oberlin College, where I'm told he also, yes, he played clarinet in the band. Because Oberlin is known for their music program. He received his PhD from Harvard in physics. And, you know, I could go through his career, but I don't want to embarrass him, but he's like one of the key people in the area of infrared astronomy. He's been a principal investigator on many different instruments and missions. So without further ado, he has an event this week that he's going to tell us about regarding the Spitzer Space Telescope. I give you Regents Professor George Rieke.
So, thank you all for coming on such short notice. Our students would not have done nearly as well. So, I hope you remember the infrared picture. It showed maybe not your better side, your better wavelength, and we're going to come back to that later in the lecture as we go on. But I want to start going way back in history. Infrared astronomy actually started in 1914 when Koblenz developed this very sensitive detector. And it was sensitive because he mounted in a vacuum, so it was isolated from heat from the outside. And he actually measured more than 100 stars and a couple of planets and published it in the Astrophysical Journal. And that was a real benchmark. It was the first photoelectric photometry at any wavelength, as well as really the first good infrared astronomy. Well, a few years ago, you remember the Year of Astronomy? I tried to promote the 100th anniversary of infrared astronomy, and unfortunately, this just didn't catch on. I thought this, oh well. And after all that, there was a big effort with the 100-inch on Mount Wilson, very impressive measurements up to through 1929, 1930, and then nothing happened. You know, we always say you invent the technology and astronomers will rush out there and use it for new discoveries. The technology sat there for 30 years and nobody really did anything with it. And this is where Arizona comes in. In the 1960s, the Lunar and Planetary Lab fell under the directorship of Gerard Kuiper, who was a pioneer of using infrared methods to look at the planets. And Gerard then hired Harold Johnson, who had invented infrared photometry of stars. And at that point, Frank Lowe was a brilliant inventor who almost hero worshiped Harold Johnson. So Frank came where Harold was, and ironically, he came in support of the radio telescope that we've now taken possession of on Kitt Peak. So the 50 years of radio astronomy actually intersects with the story of infrared astronomy. The problem is, at that point, I don't know if Yancey will tell you this, but that telescope could hardly detect anything. And so Frank fairly quickly migrated to infrared astronomy to work with Harold. But there was a problem. These were three 250-pound guys with bigger personalities than that. And so it wasn't a stable configuration in one lab. It was sort of like you tell you about a planetary system with three massive planets. One planet's going to get ejected. And that was Harold. So Harold spent about 4 years here, and then he was off to do other things. But in 1970, this group started to invite postdocs. This was actually taken for a National Geographic study on infrared astronomy. And the guy wanted, I'm transferring liquid helium, and to transfer liquid helium, if you do it right, there's no plume. And so we did one that way, and the photographer said, no go. We got to have a plume. So I did a really bad transfer, and he took the picture, and there we go. Okay. Well, that was really exciting because the field was just starting, and there were lots of things that you could observe at 10 microns, which is where this camera works. And you could see how different things look at 10 microns. I think you're saying, thank God I don't look like that. But there were lots of discoveries to make. It was really an invigorating experience. But there was a problem, which is not only you, but if you remember in great detail, even the chairs were glowing in those pictures. And so you go to a telescope on the ground, it's glowing bright in the infrared. It's just heat radiation. Furthermore, the atmosphere is glowing in the infrared, and the atmosphere doesn't even sit still. It's got wind blowing past the telescope. And so observing from the ground at 10 microns, I liken to trying to detect a match in a blast furnace. You've got this big background, and it's moving around, and you're trying to detect, if you work it out, a signal that is about 1/1,000,000th of the total signal that's coming into your detector. And so that was a real challenge. We learned how to do it pretty well, but what you'd like to do is cool the telescope down. There's the match. It really helps. So why don't we just do that? You thought this was my drinking water, but this is actually a lecture prop. Feel the outside of this. It's wet. Yeah. So if I cool the telescope down, water's going to condense on it, and I won't be able to observe. So the only way to do this, to get this big advantage, is to go up into space. And then you can cool the telescope down because you're in a vacuum. And in fact, it took almost no time for someone to propose a telescope cooled with liquid helium to go in the space shuttle and provide that big benefit. And about 10 years after this, NASA actually started a project called the Shuttle Infrared Telescope Facility, and it even made the cover of Physics Today. It had to be a real project, didn't it? And this was to be cooled by liquid helium. And when it was conceived of, people didn't believe you could make liquid helium last long enough. It had to be in a dewar, like a thermos jug, with a vacuum to protect it from heat and all kinds of protective measures to keep the heat from getting in. And so the idea was the shuttle would take it up there, you'd observe for 2 weeks, what they called an extended shuttle mission. Then they'd come back down, you'd refurbish the telescope, reload it with liquid helium, and go up again. Can any of you think of anything that's wrong with this concept? Cost. It was in the day when it was thought the shuttle would be safe, cheap, and frequent, and clean. Because just like my drink here, if the telescope is cold and the shuttle is oozing stuff like, where's the outhouse for the astronauts, it's going to condense on the telescope, and you'll just overcome the whole advantage of going to space. You'll defeat it. What's amazing to me is how many people said, ooh, this is a great idea. And it was a terrible idea, but it at least got toes in the door. I think that's its only virtue. So at about the time this came out, the IRAS mission was launched, and it had a long-life helium doer, went for nearly a year in space. So that showed this whole idea was just nuts. And so the next idea was, let's have the shuttle launch sort of, but let's put it into an orbit where it flew by itself. And notice what's neat about this. The neatest thing is we went from shuttle, infrared telescope facility, to space, infrared telescope facility, and we didn't have to change the acronym. Really important within NASA. Okay. And so, as I say, IRAS really showed that this was feasible. But there was a big problem, and that was AXAF, which is now Chandra. And so NASA Astrophysics had two big missions they wanted to promote, and they could only promote one at a time. And so the solution was to merge them into one program, which became the Great Observatories. And actually, an infrared astronomer suggested this solution. A bunch of us were invited to Washington, and there was butcher paper laid out on the table with crayons, and we were told to free associate drawings of what it would mean to have more than one observatory in space. So here's a bunch of scientists that probably hadn't had crayons in their hands since they were 7 years old, scribbling on the paper. This went to a really skillful artist, and he put together basically an adult comic book. And this is one page out of the comic book. This was to make the point that you need all these wavelengths to have complementary views of things in space so that you could actually understand them. And here's another sample with these kind of neat-looking, cartoonish telescopes, including on the ground, looking together at various things that we might want to study and understand. And this was very successful at establishing the Great Observatories as a program. It actually saved us when at one point we went through lots of travails, which I'm not going to tell all of them because you'll go home depressed, but we got canceled once, and NASA kept the program going by inventing a detector development program. And I asked the guy in charge of it who did this years later, Leonard Fisk, and he said, I felt an obligation to complete the Great Observatory. So this really came back to help us in times of need. But we were really in need. One of these two had to go first, and that was AXAF. And boy, was it frustrating for us. We sat there developing new concepts, and the new concepts never got anywhere. My optics designer for the instrument I'll tell you about at Ball Aerospace at one point said, if it's May, we must be redesigning MIPS. That was my instrument. So like every year, I went up there with a new mission concept and a new design for the instrument. And we had some hope of going until we all know about the problem with the Hubble Telescope. And I'll tell you, there's one thing you don't want. If you're NASA, that's to have your major mission become the butt of cartoons all across the country. And so Congress just didn't want to fund another mission. I mean, geez, this was the biggest mission ever, and NASA had promised all kinds of wonderful things, and it was a disaster. And so those of us involved with, sort of in those days, didn't know what to do. We came up with a couple new concepts. They didn't go anywhere, so we had a retreat, and Ball Aerospace had a facility at Broomfield, which is between Denver and Boulder, and we discussed a way to reorganize the science. And the second day of the retreat, Frank Lowe, Professor Frank Lowe, who's a research professor here, came down the stairs with a new concept. And Frank's idea was, you can get this telescope cold by just exposing it to space. Space is cold, so you let the energy pour out of the telescope into space, and then we just need a little helium dewar to cool the instruments and a little extra cooling on the telescope. There was one problem with Frank's concept. He was so possessed with the cryogenic elegance of his design that he didn't leave any room for instruments. But what do you need instruments for if you got a good telescope? Well, we eventually got that fixed. But let me show you why this is important. Europe, in the meantime, had gotten ahead of us by launching a sort of conventional infrared telescope called the Infrared Space Observatory, or ISO. And here's a drawing of it. And so it has a big, heavy shell, so it can have a vacuum. And then it has a lot of liquid helium. And then it has the telescope. And now if I take Frank's design and I just stick it in here, there we go. Look how much smaller it is. And this would be the same size telescope. It's just everything else that's been shrunk down to this much smaller design. And so our history went like this. First, I leave out the shuttle thing. That's just like a nightmare that people would sign up to that. But over here is the shuttle launched but free-flying version. Then we came up with an intermediate idea that was going to be launched by a Titan missile into a really high orbit. And then this was one along the way around, well, you've got the years on these, 1993. We were promised this would go with Congress, but it didn't. And then this is the one we finally came up with. And what's remarkable about these is the telescope stayed the same. Same size telescope, same duration in space, and look at the evolution. And unlike these numbers, which are somebody's wild guess, these are the actual numbers. I called back when we were on the launch pad to get how much it had cost to get the telescope to the launch pad, and it was $670 million. So that's why that went up. All of these would have gone up too. Look at the difference in the amount of helium. 6,600 liters of liquid helium. I have no idea where we would have gotten that. But anyway, there it is. And I should say, a key part of Frank's design was a very different orbit, and that's why we're turning Spitzer off on Thursday. The most we want to get a long way away from the Earth, because the Earth is another source of infrared radiation that will basically cause our helium to boil away. And so there was an engineer at JPL who said, why don't we just give it escape velocity from the Earth? It's very popular now to go to Lagrangian point number 2, which is neat because it's a place that's sort of gravitationally stable, but its station keeps with the Earth as the Earth goes around the sun, so you can keep the same telemetry link up to it. But it takes extra energy to get there, and we were really pressed for energy because we were going to launch on a Delta rocket, not a very big rocket, so we had to keep everything light. So I have rebuilt Johnny's favorite visual aid, a styrofoam cup with a piece of cardboard pasted on it to be the solar panels. And Johnny would go around and he'd say, hey, if we build it like this, it will be really light, and we can put Frank's telescope back here. It'll get far away from the Earth, and everything will work. And you ask, why was all this important beside just a neat way to do the mission and lower cost? And I'll tell you, I had a very interesting experience. After it sort of had already been launched and been a great success, I went to visit my sister in New York, and I took the train up from Washington, got off the train, and got in this very long line waiting for a cab. And there was a guy behind me with a very obnoxious voice. And I turned around to see who it was. And there are a couple of imitation alligator skin boots. And I look up, and it's Dan Golden, who was the administrator of NASA when Spitzer was approved. I say, this is an opportunity to get an interview. So I thought carefully, and I said, I introduced myself, said I'm leading an instrument team for the Spitzer telescope. I'm really happy to meet you. And there's one thing that has always puzzled me. What was it that caused you to give the go-ahead to go ahead and build Spitzer? And he said, it was two young kids at JPL that came up with the idea of the solar orbit and the radio-cooled telescope. And so, two young kids. Frank, when he came up with this idea, was 60 years old, and the solar orbit was a very senior engineer at JPL, Johnny Clock, who was maybe 10 years younger than Frank. But it was such a neat quote, because it tells you it's not just solving the technical and financial problems, it's somehow convincing just the right person that what you've done is neat. So, that got us started. And since we were a major center of infrared astronomy, we actually won the contract to build one of the instruments. And so this is your introduction to the multiband imaging photometer for SIRTIF. Fortunately, when it got changed to Spitzer, we didn't have to change the S. So we were still MIPS. Acronyms were preserved. And this had to be a very small instrument because even though we persuaded Frank we needed a little room for the instruments, it wasn't very much. And so along the way, some of the very first 3D printers became available, and Ball Aerospace, who was the contractor for this instrument, made a 3D print model of the instrument, 1-to-1 scale. We actually used it for things like cable routing, so it had to be an exact facsimile. And so to get an idea of the size, this is the size of the MIPS instrument. I wish I could get it back, but it's more than an astronomical unit away, so it's going to be kind of hard to do that. But this is what it looked like. Of course, it was all in aluminum. And to give you another feeling for scale, the telescope, although we kept it the same size, it wasn't big. It is 85 centimeters long. So here's a meter stick, and this is how big the telescope is. Now, we're working on telescopes that are bigger than the inside of this lecture hall. So just think of the scale. This is the telescope, and I'm going to tell you some of the wonderful science it did. I guess it's still doing it for 3 more days, but and just think about how small the telescope was. And that's all because of the incredible gain of getting into space and getting rid of all the infrared background so that you can see much fainter than you could possibly see with a ground-based telescope, even a big one. And I see my boss is here. I'm going to tell him that Spitzer is more sensitive than even the biggest ground-based telescopes. I'm sure I'm going to get an email from him about that, but it's true. We'll come back there. Okay, here are the instruments mounted in the bottom plate of the Dewar. And of course, the prettiest instrument is here. And it's next to this ugly thing. I don't know, well, that's the IRAC camera, which is actually the one that's kept going for the 16 years. And so this kind of puts a scale on it, but I want to tell you a story about this because every one of these missions has a couple of really close calls, and we had a very close call not too long after this. The first thing I have to say is shortly after this picture was taken, I got in the clean room at Ball and I saw the instruments all arrayed, nobody near them. It's an awesome sight if you've spent much of your life designing one of those instruments. And it's awesome to know of the incredible human effort to try to make something that's never been made before and to make it perfect so it's going to work. And so I said a prayer. But the prayer was, please God, let me never see my instrument again. Why did I say that prayer? Because the lid was going to go on the doer, and it would only be if something went seriously wrong that they would open it up. So that's kind of the story of this. You build it, you hand it over, and unless something goes really wrong, you're never going to see it again. Cross your fingers. So what happened, we got all the instruments in, got the vacuum in the door, loaded it with helium, and then the holidays came along. And so the engineers at Ball set up a system where they could monitor the door from the comfort of their living rooms. And something didn't seem quite right. The temperature kept climbing a little bit, and they sort of said, well, it must be temperature sensors, can't be anything seriously wrong. It turns out there's something that can go seriously wrong with a liquid helium door, and that is liquid helium is so cold it freezes air. And a door has a neck tube that the helium, or plumbing, that the helium is supposed to vent out, and if you freeze air in that plumbing, you have converted your door into a bomb. Because the helium will keep boiling and the pressure will build up and eventually it's going to explode. And it turns out that's what had happened. And we realized it just barely in time and got the ice plug out and got it relieved. And there was one person in the world that knew things were going wrong, and that was the technician who had been assigned to go in every day and write down all the numbers for temperatures and pressures and so on. And I interviewed him afterwards, and it was so stressful that months afterwards, he broke down in tears because he could not, he knew what was going on, but he could not convince anybody. And it's kind of a lesson. We brought in consultants on how to avoid serious mistakes afterwards, not before. It's kind of a lesson. It's very hard for people lower down in an organization to convince people higher up when something is really wrong. And that was his experience. Well, anyway, there's more than one close call, but what was really impressive about it is the project said, okay, we survived this and we just moved on, and there were no recriminations or anything about it. So here we are, door, telescope. There's still shrouding that has to go around it, but again, to give you an idea of the scale of what we built. And now, any good talk has the book pitch, right? So I wrote a book about this, and I didn't remember all this stuff. I went back and reread the book, but so there we are. After a launch, NASA never wants to name a telescope after anybody until it's been shown to work. There is an exception on that. That's the James Webb Space Telescope, but let's hope that it's not a bad omen. Shortly after launch, SERTIF was renamed the Spitzer Space Telescope, and it observed from 3 to 200 microns for 5.5 years, and then the helium ran out, and the rate of cooling was still good enough to keep the two shortest wavelength detector arrays in that ugly thing you saw next to my beautiful instrument, the IRAC, and that's what's been going for the last 12 years. Now there's another story about the 5 years, because there's always a problem with these missions of keeping in touch with Congress and congressional staffers, because they're the ones that basically control your fate, because they control the money. And so we would frequently meet at NASA headquarters so people could, at their own expense, stay an extra day and fan out and talk to congressional staffers. In one of those meetings, Jim Houck, who led the team that built the spectrograph, was called up to visit Dan Golden, the infamous Dan Golden of the imitation alligator boots, but at that point he was the NASA administrator. And Jim had come up with a concept for his instrument he called Bolt and Go, that you could make the parts so accurately that you had to test the alignment, you didn't have to have any adjustments. And so he took it up to Dan Golden, and Dan Golden evidently said, at that point we said we'd have a 2.5-year mission. Dan Golden said, this is much too marvelous a mission for 2.5 years, make it 5. And so Jim Houck came down to where we were meeting and told us this, and the result was the most peculiar discussion I think I've ever had. We were so used to downscoping that the discussion was, must be a trap. I think he's preparing to cancel us. And it went on and on along that very paranoid fashion. You know, we were so demoralized by just continually being asked to make it smaller, do more with less, and so on. We finally decided, okay, we'll make it 5 years, but we won't change anything that you can see from the outside. And so that's how we got to 5 years, and lo and behold, it went for 5.5. So we achieved that. And let's understand the gain this made. So here's a plot of a metric that tells you basically the mapping speed of an infrared telescope with detectors. And so here's the work of the postdoc working for Frank Lowe using the 61-inch telescope up in the Catalinas. It was the world's best infrared telescope for many years. Frank used to brag that it was much better than the 200-inch telescope. This did not make him very popular at Caltech, but it was true. So I started, made a better instrument, and that was it. Turns out that instrument was completely background limited. There was no way I could have made a more sensitive instrument on that telescope. Here is the IRAS survey on this metric. Here is the ISO instrument, the European telescope. Here is Spitzer. You talk about computers doubling their power in 2 years. We did it every 9.5 months. From when I came into this field, every 9.5 months, the capability for infrared astronomy has doubled. It's just incredible. And so that is this tremendous gain that was made by having this tiny little telescope that's cool and in space. So I'm now going to go on for the next 12 hours to tell, no. I decided I'd just give you a scrapbook of some of the really neat observations that were made. So let's start. We're going to work our way out. Ring around Saturn. So you thought that Saturn had a really impressive set of rings. Here they are. Here's a blow up, and Spitzer, my instrument MIPS, discovered there's this huge ring, which must have been that two asteroids or something that were in orbit around, distant orbit around Saturn, ran into each other and blew each other to smithereens, and the dust from them went into this huge ring around Saturn. So next time you look at Saturn, think about it having a ring that basically rivals the size of the moon in shape, in size, angular size on the sky. Okay. The marvelous thing about astronomy is you build an instrument to a bunch of requirements and a certain bunch of science that is really the most important science you can do. And once you get it going, somebody finds science is much more important and much more interesting, and they use it for that. And so Spitzer has become the go-to observatory for observing planetary transits. So when a planet goes in front of its star, You can look at how it blotted out the light of the star and how much light got past the planet, and deduce a lot about what kind of planet it is, how big it is, what kind of atmosphere it has, all kinds of interesting things. And the most dramatic example is this transit curve. And so this is the light of the star, the sort of constant noisy looking, and then all these dropouts are planets going in front of that star. How many are there? 7. Here they are, all decoded with their particular transit marked. So this is an incredible planetary system. In fact, it doesn't actually look like this, but this gives you some idea of how many planets there are. And you've heard of this system probably. It was discovered by some Belgians who named it after their favorite beer. So this is TRAPPIST-1. It's a good thing it wasn't American astronomers. I can imagine Budweiser-1. Anyway. This is very fancy beer. A bottle of this beer costs about $6. And just to put a scale on this planetary system, the star is much lower energy than the sun. So to have the same equilibrium temperature, the planets have to be a lot closer to the star. And so here they are all lined up at equivalent distance for equilibrium temperature compared with our planets. And you can see there are a number of planets that are, and they're also about the size of the Earth, all of them. So this is correct size scale. So there are a bunch of planets that are terrestrial planets, presumably very much like the Earth geologically, I'm not going to say in all respects. And they're in the habitable zone right around where the Earth is on the sun. So tremendous, interesting discovery. But there's more you could do with this kind of observation if you have an infrared telescope. And that is, when the planet goes behind the star, you're seeing the surface of the planet that's heated by the star. And in fact, as the planet goes around here, you see more and more of that. And you can actually make a temperature map of the surface of the planet. Not a really detailed map, but how else would you do this? And in fact, here is a temperature map of an exoplanet. And it looks kind of funny because this should be star-facing longitude. I grabbed this off the web, and that's really not quite right. But the maximum temperature is offset. Well, think about what would happen if you looked at the Earth. The maximum temperature in our atmosphere would not be at noon. It's like 2 or 3 in the afternoon, and that's because you have some thermal inertia and you have winds. And so this has been interpreted to show that this planet has a dense atmosphere and very strong winds that are basically circulating away from the part that's directly heated by the star. Here's another example. And this illustrates why this kind of, getting involved in this kind of thing is so neat. I had a postdoc, Zoltan Belog, that called me into his office once and said, there's something wrong with these images. I just can't get these funny things coming out of the images. I process and process. And in fact, this is the way young scientists are trained these days. That is, to get science out of something, you have to put a lot of work into image processing and manipulating the image. What turned out, what Zoltan had discovered is these are young stars. They're in a cloud where all the stars are maybe 2 million years old. So they've just formed, and they have gotten too close to really luminous hot O stars. And they've gotten so close that the heat of the O star is causing the protoplanetary disk to boil off into space. So this is the death of a potential planetary system. In all of these cases, once we knew that these were not something wrong with the instrument, this was real interesting science. Lots of other cases were found. Here's an O-star. Here's one of these tails. Up there, you can see the O-star in the tail, and the O-star is not in that picture. One of these is the discovery picture that Zoltan thought something had gone wrong with the instrument. I mean, it was that simple. And the critical role of an old guy on these projects is to wander around and say, I think that's a discovery. Stop working on it. Let's publish a paper. And so that's what happened. Next example, and I saw Kate Sue and Carl Missel come in here. They are part of the original MIPS team that have stayed to work with us on NIRCam for JWST. And this is a slide from Kate. It's something she's been tracking. Planets get built through huge collisions of asteroids. And in fact, you know, the Earth, the moon got formed when a protoplanet about the size of Mars slammed into the Earth. And when that happens, there's a lot of dust that gets thrown out into circumstellar space. The star heats up that dust, and so you get an extra infrared signature on top of what the star should do. And what Kate's been studying is a bunch of stars where that infrared signature keeps changing. And that tells us there are ongoing collisions between really big asteroids. I mean, hundreds of kilometers, hundreds of miles in diameter. They keep running into each other. And so this is sort of the process of planet construction or destruction. We don't know which, but it's related to those processes. So Kate thinks there's an impact here. We didn't see it because Spitzer can't observe any given point on the sky all the time. So there are eruptions, but when we can observe it, we saw this big increase in the amount of infrared radiation, so a lot more dust. It decays away. She promises me there was another impact here. It better be right. And then there's this gradual buildup, and then a decay, which we're still kind of struggling to understand, and then another impact. So this is a star where there's this continual chain of impacts, and the asteroids in this star must have been stirred up by something that's causing them to go in chaotic orbits where they run into each other, because thank goodness this is not happening in the solar system. If it were, life would be a lot more interesting because there would be debris from these coming toward the sun and the Earth. So this is a very active system. This system is about 35 million years old, and it's right in the period of the evolution of the system when the moon formed in the solar system. So some of these may be smaller scale, but similar to the impact that broke the moon off from the Earth. And here is an artist's concept of how this might look. There's been a big impact here. Wouldn't it be neat to go there? Well, maybe not. It's probably pretty dangerous. There's a lot of rocks flying around in space. Okay. All this is pretty close to home, but astronomers confidently predicted that there's nothing a telescope this size could do that would be of any interest for high redshift cosmology. Forget about it. And in fact, there was a big report written as part of building the case for JWST that had a paragraph in it that said, because SIRTIF is not going to be any good for cosmology, we need this bigger telescope. I mean, we almost killed the guy that wrote that, but so here was the first sample of very high redshift galaxies detected by SIRTIF, and this was a discovery by Ichiyagami, who's also in our group and still with the NIRCam project. This is a gravitational lens system, and these funny little smudges look very insignificant, but they are gravitationally lensed images of a galaxy at a redshift of 7. So they're amplified by the gravitational field of this cluster of galaxies, and they're in the way, but I'm afraid it comes with the territory. And so there are all these different wavelengths. There's a source here that had to be removed to be confident of this, and it's been removed here, and you see these two gravitationally lensed images. maybe they don't look very impressive, but if you're a cosmologist, redshift of 7 galaxies are impressive. And in fact, Spitzer has turned out to be a central part of identifying high redshift galaxies. Whenever somebody has a candidate, they have to get a Spitzer image. And the reason is, this is the spectrum of a very high redshift galaxy. These are the points you can get without Spitzer. And people publish these sorts of points all the time and say, this is a really high redshift galaxy, but other astronomers say, well, prove it. And the problem is, this could, for example, be a couple of bright emission lines in a galaxy at a different redshift. There are all kinds of ways you get a false identification. These are the Spitzer points, and so they confirm that this is the right identification. And that's been, again, a very important application. What next? Anyone want to hazard a guess? How do you follow this act? There you go. So I remember we had a great party. My program manager, Debbie Wilson, was great at finding money that we could have parties to celebrate major events in the life of MIPS. And so when we delivered it, Debbie threw a really great party. She got the foundation somehow to find money for it. And I stood up and I said, you know, this is great, but the real measure of our success will be if they go out and build something even better. And so here it is. Remember, each one of these segments is a lot bigger than the Spitzer mirror. That kind of puts a scale on how big JWST is. And if we look at this plot I showed you, so now here's the growth in this metric. That's the power of mid-infrared telescopes and detectors. It just keeps going, and the time scale has gone from 9.5 months to 10 months, doubling time. It used to be 9.5, and then we delayed the launch, and it went to 10. So this has been a really heady experience for me. I came in just at the right time, and we're going to have 50 factors of 2 over my career. A truly incredible experience. But there's another thing that's important. What makes JWST possible on that big scale is Frank's invention of cooling the telescope by radiating off into space. If JWST had to be inside a helium door, there'd be no rocket, no set of rockets, nothing, no way we could get it off the ground. So we go all the way back to our move of desperation at Broomfield of what the heck are we going to do to get this mission going? And it sowed the seeds for a much bigger, more capable telescope. And this is what's grown out of those seeds. But there's something else really important. Now, before Frank's invention, infrared telescopes in space were very limited in size because they had to fit inside helium doors, which had to have vacuum walls, which had to be very heavy, and you just couldn't put a very big telescope in that. And you'd say, hey, when Frank told us how to cool it off by radiating the energy into space, why didn't you make it bigger? Remember, we were paranoid. And we were really afraid that if we changed anything to make it look more ambitious and more expensive, we'd get canceled. And we had been canceled previously and then recovered. So all the telescopes were less than the size, the length of this meter stick. And so here we go. Diameter of the telescope, Spitzer is the high point. This is WISE. There's JWST. And that's important because the resolution of a telescope gets better in proportion to the diameter of its mirror. So here's an image of JWST that's it's sort of like, given an arbitrary distance, how it would look to Spitzer at 24 microns. And here's an image of how it would look with JWST looking at, well, never mind. It's an artist's, no, it's my concept. It's a poor scientist concept to dramatize the improvement in resolution, and that is really critical. That opens up, it isn't just the sensitivity, it's the resolution and the power of the instruments that opens up a whole playing ground for wonderful new science. So let's review. How do these two telescopes relate? Spitzer, because it was small and had no things that had to unfold, was very agile. It took 3 minutes for Spitzer to slew across the sky and point at a new object. So it did lots of very sensitive surveys. It's a lot like if you dial way back in history to the Palomar 48-inch, which was the big survey telescope, big field of view, very efficiently covered big areas of the sky. And JWST is sort of like the Palomar 200-inch. You're not going to use it for big surveys. You're going to use it to bore in on individual sources. And to give you an idea of the scale, I hunted everywhere and finally found a picture with a human being in it to compare with this famous picture of a human being with the 48-inch, just to give you an idea of the scale of these two telescopes. And so that's kind of the relation of these two missions. In other words, it isn't correct to say that JWST is going to make Spitzer obsolete. Spitzer actually has laid the ground of surveying many square degrees of sky, out of which JWST can pick the most interesting region. But now I want you to carry this thought away, if there's no other thought. And that is because of the big advantage of cold telescopes in space, once JWST is done, we will have no way to reproduce its results. It will be much more sensitive than anything we can do, even, pardon me, Buell, with 30-meter ground-based telescope. It won't be able to approach the sensitivity. So these two telescopes are going to leave us a legacy for infrared astronomy that we're not going to be able to reproduce in any way other than building another cold telescope and launching it into space. And that legacy will be for decades, I don't know, maybe even centuries. So they really are an important benchmark in our exploration of the universe. And that's where I want to stop. That's the thought for the night. If you have questions.
Thank you, George. Any questions for Professor Rieke?
So the helium lasted for 5.5 years. So what is it that causes the telescope to be closed down now?
Really good question. It's because, we'll take Johnny's prop here, there are avoidance rules for the sun. You have to keep the solar panels pointed toward the sun, and you can't ever let the telescope point toward the sun because the back is all treated, it's black, and if you heat it up, the helium, the cooling is just gone, right? And very destructive to the telescope. There's no helium left, but it just goes. So we've gotten around to where, oh yes, and the other important point is the data gets sent back to the Earth with an antenna that's bolted to the bottom of the telescope. We were really cheap. No antenna steering or anything for us. You steer the whole telescope. You cannot meet those restrictions and point back at the Earth anymore with the antenna. We're getting to where that's true. We've gone far enough around. Remember, this is in a trailing orbit that's behind the Earth, and it's more than an astronomical unit away from the Earth on its orbit. So we cannot, soon we'll be at the point where we can't send the data back to the Earth without violating the pointing restrictions.
Has Spitzer ever discovered any signs of exomoons?
So my hearing's really bad. Will you repeat?
Exomoons.
Exomoons.
Yes.
So I don't know that we've discovered many exomoons, but it's really interesting. There have been people that have projected that exomoons could be actually brighter than their planets under certain circumstances. So that's an interesting possibility. They're small, which makes it hard, but I think with enhanced transit capability, that would be a very rich field. And again, if Spitzer's been good at transits, JWST ought to be really good, right? So that's a good way to find them.
Oh, we have a question at the back of the room.
Yes, given the expense that's involved in the JWST, are there any plans for, okay, let's go with the Europeans and let's pool our resources, our money to actually, get a
So,
bigger and better telescope?
well, JWST has a lot of European involvement. It's kind of funny. Originally, I'm involved with an instrument called MIRI. It's the one that actually works at 10 microns. My wife, otherwise known as Regents Professor Marcia Rieke, is involved with NIRCam, which is another one of the instruments. My instrument is half provided by Europe, and the third instrument, NIRSpec, is completely provided by Europe. But at one point, my instrument was going to have a helium doer that would be provided by Europe, and that was scary because they didn't know, a hydrogen doer, I'm sorry. They didn't know how to make a hydrogen doer. They never made one on the scale that was needed. And so the NASA head of space science had this idea, let's trade the hydrogen doer, we'll take that because we know how to do it, for the rocket. And so Europe is supplying the rocket. We're going on an Ariane rocket. That was very unpopular with the United States rocket manufacturers, and there was about a year of fighting over that, and it looked like it might even kill the project, but eventually it got sold. So there's a lot of European involvement. It makes things from a management point of view much more complicated because we have very different cultures for how we build stuff, but it's worked. We've got the instruments, and for big projects on this scale, I think international collaboration is basically essential. They become things that humans do rather than things that a country does.
Are they going to actually dispose of Spitzer at all, or is it just going to sit there forever?
Would you repeat that for me, Tim?
Are they going to dispose of Spitzer anyway, or is it going to sit there
Oh, I don't know. Debbie Wilson, my manager, and I are going over to JPL, and I expect there's a big switch on the wall. Somebody's going to go over and, no, they'll do something different from that. And we'll find out then. It's unlike Earth satellites where you have to worry about disposing of it. It's not going to come back. Well, it will come back in a couple of 100 years. But that's someone else's problem. So I think they're just probably going to just let it tumble.
One more question.
Spitzer has a beryllium mirror, and also James Webb will have a beryllium mirror. Why do you use beryllium for the mirror? And you do coat it with gold?
So the question is, why use a beryllium mirror? And the answer is, there are two parts to it. One is beryllium is very, very low density, and so you can make a very lightweight mirror. It's low density and very rigid, so it's a way to make a very, very lightweight mirror. The other thing is when you make beryllium cold, its coefficient, thermal coefficient of expansion basically goes to zero, so once you get it cold, the mirror is very, very stable. The problem is, when we did Spitzer, people didn't know how to make mirrors in beryllium, and so there was a huge advance for JWST of learning how to make big, very accurate mirrors. But once that was solved, beryllium is a very good method for very lightweight, high-performance, cold mirrors.
Okay, last question here.
Has there been physics, or will there be physics to try to create a infrared sensor that doesn't require cryogenic cooling?
I don't think it's possible at this level of sensitivity, and the reason is you have to be sensitive to very low levels of energy. And when you heat something, temperature or something is just the energy of the molecules vibrating around. And when that energy rivals the energy of the photons you're trying to detect, it's all over. You can't make a detector. There are infrared detectors that don't have to be cooled. Here is one, but they don't have anything approaching the performance of the ones that you cool down.
All right, if we don't see you this Thursday night, we hope to see you 3 weeks from tonight on the 17th of February for Dr. Shirley's talk on radio astronomy in southern Arizona. The telescope is open for your public viewing pleasure, and I'll stamp student assignments down here.
Remember to ask Yancey what was discovered with the 12-meter telescope on Kitt Peak, and see if he knows the answer is nothing.
Let's thank Dr. Rieke one more time.